All right, folks, we have come to section 5.5, which is called Zeros of Polynomials. And with what we've learned about polynomial division and what we've learned about factors of polynomials and, sort of the x-intercepts of the graphs of polynomials and stuff, with all of that, it's been sort of building up to this section where we're going to finally formalize these ideas and establish how you factor polynomials and therefore how you solve polynomial equations. Okay, so you have in the past learned things like the quadratic formula, right? Just a few sections ago we learned the quadratic formula. You've probably learned it before. And that is like a surefire way to solve a quadratic equation. But if you want to solve higher degree polynomial equations like 4, 5, 6 to 6th degree polynomials, then you need other methods. This section is going to provide some methods for doing that. And it's going to start with two really important theorems. The first one's called the remainder theorem. It says, if a polynomial f of x is divided by a polynomial of the form x minus a constant, x minus k, which should sound familiar because we just talked about synthetic division, all right? Then the remainder that you get from that division equals f of k, which would be the function value at k, right? Like if you were to actually stick in a k. So we're going to do a quick proof of this theorem. Why is this true? Well, division, when you do that division, f of x divided by x minus k, it will yield something of this form. F of x equals q of x, the quotient, multiplied by x minus k, because that's what we were dividing by, that's the divisor, and then plus r. Now, this r, this remainder, must be constant. How do we know that it must be constant? Well, I explained when we were doing long division that the remainder that you get from polynomial division is going to be, it's going to have a degree that is strictly less than that of the divisor. So if our divisor is x minus k, right, if we're dividing by x minus k, that has degree 1. And the only type of polynomial with a degree less than 1 would be degree 0, which is constant, right? If the highest power of x is x to the power 0, that's a constant function. So that means that this remainder is just r. I'm not going to write r of x because it's not really dependent on x. It's constant. That is essential to the proof of this theorem, because then what we can do is say, if you do f of k, right, f of k, the function value, stick k in here for x, and you get q of k, whatever that equals, times k minus k, which will be 0 plus r, right? So that's q of k times 0 plus r. This whole thing is just 0, so that equals r. And look, we just proved, so therefore, f of k equals r, the remainder. So why is this useful? Well, let's do a quick example. Let's say you take the function f of x equals 6x to the power 5 plus 2x cubed minus 6x squared minus 10x. Let's evaluate f of 2. We're going to use the remainder theorem. So we could just stick 2 in there. Sure. But we can also use the remainder theorem to evaluate this. And what we're going to do is, instead of actually evaluating f of 2, we're going to divide by x minus 2. Okay. And to divide by x minus 2, I'm going to use synthetic division. This isn't, by the way, I just realized as I'm doing this, this isn't actually a very good example of why this is useful, but this is an example of how to use it. I kind of forgot what my intent was behind this example before I started showing it, but yeah, this is more how you use it. As for why this is useful, that will become evident soon enough. But okay, so we're going to do synthetic division with the number 2 on the outside over here, and then we're going to write all the coefficients of this polynomial, but I've got to make sure that I write them all of the powers of x from 5 down to 0. So that in particular means, I'll start with the 6, but then we were missing x to the fourth, so the next number is 0, x to the fourth. And then it's plus 2, x cubed, minus 6x squared, minus 10x. And then actually we have one more number to put in this list because there should be an x to the 0 power term, which would be our constant term, and that is a 0. So I have to make sure to stick that 0 at the end over there. So there we go. I've got the full list of coefficients, and now I'll do synthetic division. I'm not really talking because I'm just doing synthetic division here. I'm just, I guess I'll remind you how to do this. Drop this down, multiply it by 2 and put it here. Add this column, multiply by 2 and put it here. Add this column, 26, multiply by 2 and put it here. I'm going to stop describing this because I'm worried I'm going to make a mistake. I'm just going to copy what I did on my notes and hope that I did the arithmetic right last time. I'm pretty sure it's, well, if it's not, I'm sure someone will catch me. You get the idea, even if my addition is not correct or whatever. 0 plus 164 is 164. So that is my remainder, right? And this theorem, the remainder theorem, is telling me that that number is also equal to f of this number. So it should be that f of 2 equals 164. And you can check if you want by sticking 2 into this function and multiplying them, like doing all the powers and multiplying by the coefficients and adding or subtracting, and you should get the same number, 164. So that's the remainder theorem.